Hi everyone, we are Group 117. I'm Aditya. I'm joined by my teammates Prancho and Vedant. And today we are presenting our work on private and keyless ML inference for open radio access networks. This project is based on extending a recent paper from IEEE Diceman 2024. So the overview is that we have built an paper that looks at how machine learning can work within open RAN systems while keeping user data private. Our work focuses on enhancing this setup by improving the inference speed and balancing performance with privacy and latency. So let's take a look about what Open Radio Access Network really is. So ORAN or Open Radio Access Network is an open vendor neutral version of the traditional cellular network infrastructure. So the key part here is the RIC, the near real-time controller, which runs small ML apps called X apps. These apps use real-time data to help optimize network performance, especially through the E2 interface. And they talk to each other using internal messaging. So now let's take a look at what XApp really is. So our XApp is we've built an ML based XApp that classifies types of interference in the network. It takes raw signal samples and then turns them into images called spectrograms and classifies them to detect what kind of interference is really happening. And based on the result, it sends back controlled messages to the RAN to make improvements. While we are at it, let's also take a look at our data set that we will be using for this project. So we used a data set of 2100 spectrograms, evenly split into three classes. So we have clean signal, SOI, we have continuous wave interference, CWI, and chirped interference, CI. All data was normalized and encrypted to make the task more realistic. These samples came from actual hardware setups using MATLAB and USRPS. So we are using vision transformers. So our first model was a vision transformer. It divides into small patches and embeds them into vectors and uses self-attention layers to capture relationships between the patches. It gives good accuracy but has a higher processing time in general. Um, Apart from that, the hybrid convolutional transformer, it combines CNNs and transformers. CNNs are good at capturing local patterns, while transformers are really good at global relationships. This model tries to get the best of both worlds. Fast like CNN, small like transformers. Apart from that, we have used the connext model. So it's a modern CNN that borrows ideas from transformers like bigger filters and better normalization, but also keeps the speed and efficiency of the CNNs. It outperforms older CNNs like ResNet and can match transformer performance with lower complexity. So the evaluation metrics we have used is like standard ML metrics like accuracy, precision, recall, and F1 score. We also measured inference time, meaning how long it takes to classify each spectrogram, which is really super important in real time systems. Let's take a look at the graph for the baseline. So these are the results that were given by the baseline, and our baseline model using the original vision transformer got around 81% accuracy. It did best on the clean and CI signals, but struggled a bit with the CWI interference. Overall, the model was well balanced, but not exactly really fast. This was our final model. You can take a look at the results. We have given the graphs here. So our final model context had a slightly lower accuracy of 71%, but it improved speed a lot. It still did really well on the CI and the SOI, but continued to struggle with the CWI. So we traded some accuracy for a much better speed. So as we talked about real-time systems, timing really becomes important. To highlight the trade-off, the vision transformer took approximately 0.082 seconds per image, while the connext reduced it to almost half to 0.046, while it nearly doubled the speed. For real-time systems like Open RAN, this latency reduction is critical, even if it means a slightly accuracy drop. That's it. Thank you.